Hello, hi everyone. Myself, I am Vaishnavi. I am from IT department as part of Tech Talk. Now I wanted to explain about diagonalization of real symmetrical 2 by 2 matrices. Now let us know what is actually the diagonalization of a matrix means. Let us consider a matrix A of some order 2 by 2, maybe of some order n, maybe 2 by 2, 3 by 3, or 4 by 4. That matrix A is said to be diagonalizable if that matrix A is similar to a diagonal matrix. We know that diagonal matrix is nothing but the matrix in which, except the principal diagonal elements, the rest of the elements are zeros, and the principal diagonal elements are non-zeros in a matrix. And let us have a look at the conditions for making for diagonalization of a matrix. First point, eigenvectors must be linearly independent. Eigenvectors, we find eigenvectors for respective eigenvalues. Generally eigenvectors are linearly independent when we have distinct eigenvalues, and in such cases, like the even we have same same eigenvalues, sometimes we get the distinct the linearly independent eigenvectors. For example, if we have if we get after after getting after finding eigenvalues, if we have a minus lambda I matrix as some 2 2 2 1 1 1 1 1 1 and x1 x2 x3 x1 x2 x3. Here, after converting the matrix into echelon form, we get 2 2 2 and 0 0 0 0. Then multiplying this with the column matrix x1 x2 x3, we get 2x1 2x1 plus 2x2 plus 2x3, that equals to 0. That equals to 0. So I erase everything. We have 2x2 2x1 plus 2x2 plus 2x3 2x3, that equals to 0. In this case, we consider we don't know the value of x1 x2 x3, so we assume two values as some k1 and k2. In this case, we get distinct eigenvectors which are linear. We get maybe same or distinct, but we get linearly independent eigenvectors. But in some cases, like let us have an example. 2 2 2, same example, but here I go with the 0 1 1 1. After converting this matrix into echelon form, in this process the matrix turns into 2 2 and 2r2 minus r1 0 0, and here 0 minus 2 into 0 0, 2 into 0 0 minus 2 0 0 0. Here r3 equal r3 tends to 2r3 minus r1, r3 tends to r2 tends to and here we have and after multiplying this into with the column matrix, that is x1 x2 x3 x1 x2 x3, we get two equations. They are 2x1 plus 2x2 plus 2x3, that equals to 0, and second equation as minus 2x3 equals to 0. Here x3 equals to 0 from this equation. From this equation x3 equals to 0, and when we substitute this x3 in equation 1, we get 2x1, we get 2x1 plus 2x2 equals to 0, and here x3 equals to 0 we have from equation 2. And now we consider x2 or x1 as some k, then we get x1. Here we have the same eigen value, maybe 1, and for that even here the eigenvalues are 2, which are of same. We have only one eigenvector, and this eigenvector is called as linearly independent one, linearly dependent one, linearly dependent, dependent, dependent. So we cannot find the model matrix, that is P. We cannot find out model matrix using only two eigenvectors for 3 by 3 matrices. So in that case, the given matrix is not diagonalizable if it is not linearly independent. I think it's clear. Now go through the second point. A is diagonalizable if algebraic multiplicity equals to geometric multiplicity. What actually meant by algebraic multiplicity? Let us know. Algebraic multiplicity, the order of lambda as a root of characteristic polynomial, is called algebraic multiplicity. We know that characteristic equation is nothing but a minus lambda I minus lambda I. If we consider, let us consider a matrix 2 3 0 4 2 3 2 2 1 0 4 0 0 0. Here it is also 2. It is an upper triangular matrix, and in an upper triangular matrix the diagonal elements itself are eigenvalues of that matrix. Here we have 2 a minus lambda I, 2 minus lambda 2 times, so 2 minus lambda whole square, and 4 minus lambda, here 1. Here if you look at the 2 minus lambda square, its order is 2. Order is nothing but power. Here for eigenvalue 2, the order is 2. then that order is said to be algebraic multiplicity. Now algebraic multiplicity of 2 equals to 2, and in case of 4 minus lambda its order equals to 1, then 1 is said to be algebraic multiplicity of 4. Geometric multiplicity. How we find geometric multiplicity of an eigenvalue lambda is how we find geometric multiplicity of a matrix. We first of some eigenvalue lambda. Initially we find the A minus lambda I matrix, then we find its rank by reducing it into echelon form, and the nullity of a matrix is nothing but rank minus 1. Then that nullity of that matrix A minus lambda I is said to be geometric multiplicity of that respective eigenvalue lambda. If these two, if algebraic multiplicity and geometric multiplicity of an eigenvalue are equal, then the matrix is diagonalizable. If they are not equal, then it is not diagonalizable. The given matrix is not diagonalizable. Here we have to note a point, and the geometric multiplicity is always less than or equals to algebraic multiplicity. Now let us know how to diagonalize a matrix. Steps to diagonalize a matrix. First we have to find the eigenvalues of a given matrix, that is lambda, and by using the eigenvalues we have to find the eigenvectors for respective eigenvalues lambda. Here I have considered a 2 by 2 matrix, so I have given here 2 eigenvectors. Then we have to form a model matrix, that is P. The model matrix is formed by using eigenvectors. Here I have considered a 2 by 2 matrix. So x1 and x2 are, suppose if x1 and x2 are eigenvectors of a matrix, then by using that x1 and x2 we form a model matrix. If x1 equals to 1 1 and x2 equals to 2 2, then model matrix P, that is P equals to 1 1 and 2 2. Okay, then after we find product of P inverse A, that is given matrix, and P model matrix. How we find the inverse of a matrix? We find inverse of matrix using the formula adjoint A by det A. Det A. Adjoint A, we find adjoint A using cofactors. Adjoint A is nothing but cofactors transpose of cofactor matrix. If we multiply the three matrices P inverse A and P, that is equals to some that is equals to a matrix. Let that be an matrix D, and D is said to be diagonalized matrix if its diagonal elements are eigenvalues. If its diagonal elements are eigenvalues, then the matrix is said to be diagonalized matrix. Here 1 and 2 are eigenvalues, and it seems to be a diagonal matrix, yes, and its diagonal elements, principal diagonal elements are eigenvalues. Then that matrix is said to be diagonalized matrix of that respective matrix. Okay, now let us look at an example. Diagonalize the given 2 by 2 symmetrical matrix. What is meant by symmetrical matrix? Symmetrical matrix is nothing but even when we interchange the rows and columns of a matrix, if we get the same matrix, then we say that the matrix is symmetrical. Here we, even if we interchange the rows and columns of matrix A, we got same matrix which is equals to A. So this matrix is symmetrical, and here we considered a 2 by 2 symmetrical matrix. We know how to diagonalize a matrix. First we have to find out eigenvalues of given matrix. We find the eigenvalues using the characteristic equation, that is det of A minus lambda I equals to 0. And here I is nothing but identity matrix, that is where except the diagonal elements, rest of the elements are zeros and the diagonal elements are 1. And when we multiply identity matrix with the lambda, we get lambda 0 0 lambda, and subtracting a minus, to find a minus lambda I, subtract lambda I, matrix lambda I from A, 1, here 1 minus lambda, and 2 minus 0 is nothing but 2, and 2 minus 0 is nothing but 2, and 1 minus lambda, 1 minus lambda, and det of this is 1 minus lambda into 1 minus lambda, and 2 into 2, that is 4 minus 4 equals to 0. 1 minus lambda into 1 minus lambda minus 4 equals to 0. 1 into 1 1, and 1 into lambda, that is minus lambda minus lambda minus lambda into 1, that is minus lambda, and minus lambda into minus lambda, that is plus lambda square, and minus 4 as this lambda square minus lambda minus 2 lambda minus 4 plus 1, that is minus 3, that is equals to 0. And we find the roots of this equation, and we get minus 1 comma 3. How we find roots? Lambda square minus 2 lambda can be also written as minus 3 lambda minus, sorry, plus lambda minus 2 lambda can be also written as plus lambda minus 3 lambda minus 3, that equals to 0. Here from these two take common lambda as common, and then lambda plus 1, and from here take plus 3 minus 3 as common, minus 3 as common, then we get lambda plus 1, lambda plus 1, lambda plus 1, and from these two take lambda plus 1 as common, and the remaining lambda minus 3, that is equals to 0, and lambda plus 1 equals to 0. For that we get lambda equals to minus 1, and lambda minus 3 equals to 0, and lambda minus 3 equals to 0. From here we get lambda equals to 3. Therefore, the eigenvalues for the given 2 by 2 symmetrical matrix are minus 1 and 3. Next step, we have to find the eigenvectors for the respective eigenvalues. They are minus 1 and 3. Let us find the eigenvector for lambda equals to -1. We know that to find eigenvectors, we use the characteristic equation, that is A minus lambda I of x, where x is the column matrix, and A minus lambda I, we have A as 1, 2, 2, 1 and 1. Here this is A, and 1 minus of, here lambda equals to -1, 1 minus of -1, that equals to 2, and 2 minus of 2 minus of 2 minus 0, that equals to 2, and 2 minus 0, that equals to 2, and 2 minus of -1, that equals to 1 minus of 1 minus of -1, that equals to 2. Here we have A minus lambda I matrix as 2, 2, 2, 2. And now for finding eigenvectors, we initially convert the matrix into echelon form. We know that to convert into echelon form, the first element must be non-zero and the below element must be 0. And in order to make the below element as 0, we have used row transformation. R2 tends to R2 minus R1, R2, 2 minus 2, that equals to 0, and 2 minus 2, that equals to 0. Then write the column matrix as it is, x1, x2, that equals to 0. Now it is converted into echelon form. Now multiply these two matrices, 2x1 plus 2x2 equals to 0. Where if we take 2 as common, then we have x1 plus x2 equals to 0. And if we take these 2 this side, then we have x1 plus x2 equals to 0. x1 plus x2 equals to 0 plus x2 equals to 0, and x1 equals to -2. Now let us consider x1 equals to k, x2 equals, here I have taken x2 equals to k. We can take x1 equals to k. From equation 1, we know that x1 equals to minus x2. Here we have x2 equals to k, then x1 equals to minus k. Then the column matrix x1, x2 equals to minus k, minus k. Take k as common, then we have -1, 1. This -1, 1, this matrix -1, 1 is eigenvector for eigenvalue -1. Now in the same method, let us find out the eigenvector for lambda equals to 3. Same process repeats. We find A minus lambda I of x. We have A as 1, 2. A as 1, 2, 2, 1, and lambda I, here lambda I equals to 3, 0, 0, 3. A minus lambda I 1 minus 3, that equals to -2. 2 minus 0, that equals to 2. 2 minus 0, that equals to 2. And 1 minus 3, that equals to -2. This is A minus lambda I matrix. And here x is column matrix x1, x2. Now let us reduce this matrix into echelon form by using row transformation. Here R2 equals to R2 plus R1, 2 plus -2, that equals to 0, and here -2 minus 2, 2, R2 tends to R2 plus R1 is to R2. Here 2. 2 plus minus 2 that equals to 0, and minus 2. Minus 2 plus 2 that equals to 0. Now it is converted into echelon form. Now it is reduced into echelon form. Now let us multiply these A minus lambda I with the column matrix X. Column matrix X minus 2 x1 plus 2x2 equals to 0. If we take 2 as common, then we have minus x1 plus x2 equals to 0, minus x1 equals to minus x2, minus cancel, and x1 equals to x2. Now let us assume that x1 equals to some k, then we get x2 equals to k from this equation. X1 equals to x2. Now we have x1 and x2. Substitute in this matrix, that is k, k. Now take k as common and we have 1, 1. Now let us name this matrix as A2, and this is eigenvector for lambda equals to 3, and we have eigenvector for lambda equals to minus 1 as minus 1, 1, and for lambda equals to 3 we have eigenvector as 1, 1, and for lambda equals to minus 1 we have eigenvector as minus 1, 1. We know that we form model matrix using the eigenvectors a1 and a2. Here a1 is minus 1, 1, and a2 is 1, 1. We find next we find the P inverse. P inverse is nothing but adjoint P by det P. Here det of P equals to minus 1 into 1, that is minus 1, and 1 into 1, 1, minus 1, that equals to minus 2. Det of P equals to minus 2. And then adjoint P. For 2 by 2 matrix we find the adjoint is nothing but, if it is in ABCD format, then its adjoint equals to D, A, and just the symbols of B and C are changed. Here from this A equals to minus 1 and D equals to 1, interchange initially. D as A minus 1 and A as D, that is minus 1, and interchange the symbols of B and C. Here 1 and comes to here adjoint P, minus 1, minus 1. Then P inverse equals to minus 1 by 2, 1, minus 1, minus 1, minus 1. Now in the next step we multiply 3 matrices P inverse A and P. We have 3 matrices. Then let us multiply P inverse into A into P, that equals to minus 1 by 2. Here this is P inverse, and comes to this is A, this is P. Now first multiply A into P. 1 into minus 1, and 2 into 1 plus 2, minus 1 plus 2, 1, and 1 into 1, 1, 1 plus 2, that equals to 3. 2 into minus 1 minus 2 minus 2, 1 into 1 plus 1 that equals to minus 1, and in the similar 1, 2 into 1, 2, 1 into 1 plus 1 that equals to 3. In the same manner, multiply P inverse into this matrix, then we get 2, 0, 0, minus 6. Then divide this with 2, minus 2, minus 1 by 2. Then we get the matrix minus 1, 0, 0, 3. And this matrix is said to be diagonalized matrix. Here we know that we have eigenvalues. They are minus 1 and 3. This matrix is diagonal matrices, right? Except the principal diagonal elements, rest of the elements are zeros. And here the diagonal elements are eigenvalues. Yes, lambda 1, lambda 2. Hence, this matrix is this matrix is called diagonalizer matrix of A. Thank you. That's all about diagonalization of 2 by 2 symmetrical matrix. Thank you.